I'm going to this short presentation on prototype implementation of new backend for the OCaml opt compiler using. Okay, I'm going to give a short presentation on a prototype implementation of new backend for the OCaml opt compiler, which I implemented using LLVM for the group generation. So, why a new backend? OCaml opt works just fine, right? It produces really good machine code, at least as long as the programmer produces good OCaml code. But there is quite a big amount of hardware-specific, platform-specific code in the compiler, and using LLVM as a platform-independent way of generating machine code might reduce that quite a bit. So first of all, LLVM, it is an optimizing compiler framework with a high-level assembly language as input in single static assignment form. That is, you have virtual registers to which you can assign a value exactly once. And additionally, the ability to allocate stack slots where you can store values and from which you can load values to implement mutability. So, first of all, the OCaml compiler, this is a schematic which you have seen already today. What I've changed is the part from C++ to native assembly code. In particular, the pipeline for this part now looks like this. So there are two intermediate representations, mark and linearize, which are modeled after the mark and the linearize representations of the OCaml opt compiler. From this, LLVM assembly is generated, which is then transformed to native code using LLVM. So the new backend has some limitations. It is only implemented from OUD 64 because that's what I had available. It is not the binaries produced by this new backend are not compatible with ones produced by OCaml opt. One of the reasons is that LLVM does not support OCaml style exceptions in any way, because to implement those, it would be necessary to explicitly manipulate the stack. And LLVM doesn't let you do this, because otherwise the analysis within LLVM would be much more complicated. So instead, I went for set jump, long jump exception handling. Another point is that implementing a custom calling convention in LLVM can be quite tricky, because LLVM, for some reason, didn't treat registers, did treat some registers as calling safe, even with a calling convention without calling safe registers. So with no binary compatibility because of the missing option to implement the exceptions, I thought, well, why use the OCaml calling convention? I could just use system-wide ABI calling convention. Well, there's another thing. The garbage collection is kind of buggy. It does work for simple programs I wrote to test it, but any really meaningful big program doesn't work. I'm not exactly sure where the bug is, because of the changed calling convention. I had to change the runtime system to use that calling convention. Then there are some things that LLVM does wrong when optimizing. So LLVM's optimizations are turned off, but I'm not exactly sure that it does the right thing even that, with optimizations turned off. And of course, my code could just emit faulty LLVM code. Then the obvious thing, the code produced by the new backend is rather slow, because, well, if you compare it to OCaml opt, it's really hard to get to this level of performance. And in addition, as I said, LLVM's optimization are turned off. Because of the way LLVM handles garbage collection, a lot of most of the time the values you work with live on the stack, so you have to reload it every time you access it and store it back all the time, so that makes it even slower. So LLVM does lack a few features to implement a language like OCaml. Especially the exception handling part is really not so nice. But also the garbage collection interface that LLVM provides is kind of a problem. As I said, all the values that most of the values need to be stored on the stack, because the only way for LLVM to treat something as a potential root for the garbage collector is to mark a slot on the stack. So everything that might at some point be a pointer has to be stored on the stack, and before every function call it has to be, if it is a register, it has to be stored on the stack and has to be reloaded after the function call, because the garbage collector might run. This might be a lot easier if LLVM changed this implementation and would do this stuff automatically. If you could just say, okay, this virtual register may contain a root, so do the right thing. But it doesn't at the moment. It does not offer a feature to say virtual register is a potential root for the garbage collection. And you also have the problem that at the beginning of each function there's a huge amount of stack slots that is allocated when you enter the function. These slots are there all the time you are in the function and are only deallocated at the end when you return. And if you have a simple sequential program that you takes a pointer as an argument, passes it to one function, never uses that pointer again, it gets the return value, which is also a pointer, and passes it to the next function, and so on. You have lots and lots of stack slots, but only one is really used at any time. So this is really inefficient. To work around this, you either have to change LLVM to handle this in a more sensible manner, or you will have to use a kind of register allocation mechanism to allocate the stack slots. One result that is kind of nice is that the amount of platform-dependent code is much smaller with the new backend. In the original backend, there are about, I think, 2,000 lines of code for the MD64 backend. Although that also includes the Windows code, which is about 900 lines, I think. And the new backend has 14 lines of platform-specific code. This is mostly for data declarations, which also a problem with LLVM can't be represented in the way they are, because OCaml uses a pointer to the first data element and not to the header. Changing that would make it possible to use data declarations in LLVM, and you could get rid of another, I think, 8 or 10 lines of platform-specific code. The other thing that remains of platform-specific code then would be declarations of how big an integer, a pointer, and a float are, and whether the platform is big endian or little endian. So, thank you for your attention.